In this segment, I'll explain the twin paradox and use the Minkowski diagram to resolve it. So we've seen before that we can find the proper time shown by a moving clock by using the formula which tells us that tau is 1 over c integral ds along the path of the moving clock. The integral in this formula has to be calculated in an inertial reference frame. So remember how we derived it. We used a co-moving reference frame that instantaneously had the same velocity as the moving object and used the Lorentz transformation to connect the time in one reference frame and another. Generally, we don't know how to transform time between non-inertial reference frames. This is a subject of general relativity. Here we're dealing with special relativity. So this formula here is restricted to the case where everything on the right-hand side is measured and integrated in an inertial reference frame. So let's consider the following scenario. We have two twins, Alice and Bob. So initially they are both at the Earth. And then Alice hops on a rocket, and the rocket travels away from the Earth. And let's assume it accelerates very quickly to some velocity v. So it travels with a constant velocity over some distance. Then it quickly decelerates and accelerates back, and then reaches the same velocity and comes back, and then eventually reunites with Bob. And let's say that Bob measures the time that has taken between the Alice's departure and arrival, and let's say according to Bob's clock, the time that has elapsed is 1 in some units. Let's say 1 year. Okay, now the question is, what will Alice's clock show? Or in other words, how old will Alice be at the time, based on her natural biological clock? So how do we calculate that? Well, we have the formula for that. So tau is equal 1 over c integral over ds. So if we substitute the expression for ds, so remember ds squared is c dt squared minus dr squared. Then we can write ds as c dt square root 1 minus 1 over c squared dr by dt squared. Now this here is the velocity, so we find c dt square root 1 minus v squared over c squared. So we would substitute ds over c into the formula for tau, and that will give us integral dt square root 1 minus v squared over c squared. Now, with the exception of short time periods at the beginning of the journey and near the crossing at the end, the velocity is constant. So if the acceleration happens quickly, it does not contribute anything to the interval. And then v is just a constant number. We can take it outside of the integral, and we'll find that this is equal to t square root 1 minus v squared over c squared. So in order to find how much time has elapsed according to Alice's clock, all we need to do is take Bob's 1 year and multiply by the square root 1 minus v squared over c squared, And obviously, we'll get something that's less than 1, so Alice returns younger than Bob at the time. Now, this is a correct calculation. We did everything as we should have. We took this formula and applied it in an inertial reference frame, Bob's reference frame. It's not moving anywhere. It's not accelerating, so we just apply this formula and find this result. Now, what would happen if Alice attempted to illegally apply this formula in her reference frame? Now, her reference frame is accelerated. It is accelerated at the end of the journey when she turns back. So if she tried to apply this formula in her reference frame, then, well, she would use the same expression. Now, t would be the time shown by her clock, and she would incorrectly conclude that Bob's clock should show a smaller time interval than hers. Now, this would be an incorrect conclusion, and we could just say that, well, she shouldn't have applied the formula in a non-inertial reference frame and stop at that. But I want to show you where the problem actually arises. Why is it illegal to use this formula in a non-inertial reference frame, and how we can recover the missing piece in this puzzle. So we'll use the Minkowski diagram to assist us. Here I have the sketch on the left. So let's do the following. So first of all, I'm going to show the world line of Alice during her outward and inward travel. So let's say that Alice departs at time equals 0, and let's set the coordinate of Earth to 0. So Alice departs in the x direction and departs from the origin at this point. Now, I'm going to draw the outward journey by a straight line starting from 0. So this would be Alice's world line as she travels out. Now, when she goes back, so we assume she decelerates and accelerates back very quickly. So on this diagram, the corresponding time that takes to reverse is very small. So then she just goes back along a straight line like this. Okay, so this is the point where she turns around. Now let's put some markings on the axes. So let's project this point to the time axis and to the x-axis. So because we know the whole journey took 1, whatever units we have, 1 year or 1 light year, then we know that this point here on the time axis is 1. So this point is 0.5. And then what is this point here? Well, this is the distance traveled by a rocket traveling at velocity v in half a year. So this point should be 0.5 v over c. Now the calculation using this formula at the top of the page is identical to using this hyperbolic Pythagorean theorem as I explained in the previous lecture. So if we want the time period corresponding to one of the parts of the journey, I would take this side and this side and write that c tau squared equals half a year squared minus half a year times v over c squared, and c tau would then be 0.5 times square root y minus v over c squared. So this is fully equivalent to the formula here and the result that we've got. So when we're dealing with the Minkowski diagram, that's all we do. Use the hyperbolic Pythagorean theorem. Now, what happens if Alice attempts to apply this formula in her own reference frame? So Alice would take the time that her clock shows. So at this point, her clock, as we know, shows 0.5 square root 1 minus v squared over c squared. And she would figure, well, Bob is moving away from me at velocity v, so then Bob's clock at this time, when I'm here, has to show tau times square root 1 minus v squared over c squared. So that would be 0.5 times 1 minus v squared over c squared. And she would figure there's a similar time period on my way back. So overall, Bob will be younger than I am when I return. So what's wrong with this picture? Well, what's wrong with this picture is that essentially at the turning point here, so this is where the problem must be, because this is the point, the only point in this figure where Alice's reference frame is non-inertial. So essentially what Alice is doing is changing a reference frame. She's jumping from one frame to another. During the outward journey, her reference frame has the CT prime axis that is parallel to the world line of her rocket. So this is the CT prime axis of Alice's reference frame as she moving out. And her X prime axis goes like this. Now, as she goes back, then she switches into another reference frame. Now, that is the one that's parallel. The T double prime axis is parallel to her backward journey, so this is CT double prime. And her X double prime axis goes like this. So what happens with Alice's way of calculating time differences? Well, when she computes the time t1, she actually computes the time that has elapsed according to Bob's clock at the time that is simultaneous in her reference frame k prime with the point of reversal. So in fact, we have to draw a line parallel to the x prime axis, and this will give us the time t1, which she has obtained according to this formula here. Now, this is a correct calculation, but this doesn't account for all the time that has elapsed on Earth. So Alice has found this time here, this time is t1, and then if she doubles that, she will also account for this time, but there's also the time period here that goes missing. Now, how does it go missing? Well, the thing is that events that are simultaneous in the reference frame k prime, which is this point and the point of reversal, are not simultaneous in reference frame k double prime. So in k double prime, this point is simultaneous with this later point on Earth. So it looks like while Alice reverses here, while her rocket reverses, during this time of reversal, which takes a very small amount of time here, Bob actually ages by this time period. Now, of course, Bob knows nothing about Alice's reversal, so it's not like he suddenly starts aging faster. It's just when Alice computes the time differences on Earth, she has to take into account this relative nature of simultaneity, and that she needs to correct for that when she uses different frames to compute time differences. So let's see how the paradox is resolved by taking this time into account. So I'm going to call this time here, I'm going to call it T2. Now, how do we find T2? Well, it's quite easy. So the angle here is the same as here. Now, if we call this alpha, then in this picture, the tangent of alpha is the ratio of this distance and this distance. Now, this distance is just half VC, and this is just 1/2. So the tangent of alpha is equal to V over C. Okay? Now, to find T2, we need to take 1/2 V over C, which is this length, and multiply it by the tangent of alpha. That gives us 0.5 V over C squared. Now then, T1 plus T2, taking Alice's calculations, so T1 here is 1/2 1 minus V squared over C squared. So let's take 0.5 outside, so 1 minus V squared over C squared, plus T2, but T2 is 0.5 V over C squared, so we simply add V squared over C squared, these two cancel, and we have 0.5, which is the correct result, the actual time that has elapsed according to Bob's clock. So there is no paradox. You can, in this case, compute the elapsed time both in Alice's and Bob's reference frames, taking into account that Alice jumps from one reference frame to another. Now, in the general case of an accelerated reference frame, one could also compute the time differences, but one would have to use the tools of general relativity, which are outside the scope of this course. So, to conclude this segment, we have considered the twin paradox and its resolution using a Minkowski diagram. The resolution involves taking into account that Alice, moving in a rocket, jumps from one reference frame to another, which leads to a missing time due to the changing simultaneity plane between two different reference frames.